There, you got another minute. All right, so it's 11:30. Let us begin.
Yes, sir. I think you're on mute.
Hmm. Shouldn't be. Can you guys hear me or no?
Yeah.
I can hear you.
Yeah,
I can hear you.
Is it just really low or?
Oh yeah, I think my volume is down. My bad.
It's all good. Thanks for letting me know, though. All right, couple things. STCW, a couple people haven't done this yet. I'm calling you out. Frank Bravo, Jerry Burns, Adam Frame, William, Cole, Anthony, Harry, Kate, Nicholas, Paul, Sterling, Matthew, Michael, Isaac. Y'all have to do that. Get it done by the end of the week. All right.
What is that exactly?
It's the STCW. If you go into the, let's see, modules. Put up the share screen. There we go. There we go. Go into your modules. There's two things in here you need to sign. One is the STCW. You're going to submit it in there. I know some of you tried resubmitting it. I'm making it so that way you can submit it unlimited times. All right. So you have to sign that. All right. And the 540 lab agreement. That's something new. I'll talk about that in a second. So both of those have to be signed and submitted. All right. And like we talked
Where
about
do those
last
get
class,
submitted?
if you don't have, say again?
Where will these be submitted?
Right onto the actual. So if you click right on it, you can see it says browse my computer. You can browse your computer where you saved the form and you can submit it there.
Excuse me, I have a question. Excuse me, I have a question.
What's up?
For the other class that you have on Blackboard, are you gonna be posting anything on there for the lab?
Oh, no, I'm not going to use that.
Okay.
They just put that there. So 540 lab is going to be physically on the ship. There's nothing there that's going to be posted in that actual Blackboard. All right. So everything that is going to come to this class is going to be only on the lecture section of this. All right.
Okay, thank
I
you.
can promise you that if it's not on this lecture or via email, I'll probably do both. Okay. Then it's not your responsibility. That lab, I'm not going to use as a Blackboard. Okay. Going right from there into lab, we have this contract right here. Like I said on Monday, all right, I wrote this up. Basically, what this states is that it's a contingency that I never thought I would ever have to write, nor I would imagine I would ever have to write something like this. All right. So, because of the way the world is with the coronavirus and everything like that, if we do not return to in-person classes, this first event is what's going to happen. All right. You have to take Engineering 540 lab no matter what. You have to take it before you go out on cruise for the first time. Okay. So if we, by some chance, don't return to school for in-person class, 540 lab can't happen because it happens on the ship. All right. So that means you are basically responsible for taking it in the next earliest semester. All right. And that plate that we talked about, that 10%, that steam tracing can't happen either because it's a tracing of the steam water cycle on the ship. So that 10% is going to be broken up into 2% for quizzes added to it. Each test gets another 2% added, and the final exam gets another 2%. All right. If we do to return in-person classes, basically you'd have to complete all of the labs. Again, this is exactly what will happen. Same description. You're going to have to retake the lab and its fruition. All right. So name, date, signature, sign it, submit it on Blackboard in the same spot. All right. For those who don't have Adobe, if you missed it from Monday, make sure you just type in Adobe into Google. All right, go to Adobe Reader. It's way better than the browser version. All right, click on the link. This is free. You don't have to pay for it. It works on Mac, Linux. It literally works on everything. Unclick McAfee. You don't need that. And then download it. All right. When you get into it, where'd the Zoom control go? There it is. When you get into it, you can use it. There's the sign button up here. You could sign the document. You could type your name into it. All right, all of that good stuff. All right. Understood? Yes?
Yes.
All right, good.
Yeah.
Feedback to me is appreciated. Staring heads is just kind of odd. All right. Let's move on with the class. Minimize that. Open this. All right. Any questions before we begin?
Just a quick question about regarding like if we are in person. I know like the lab is very shortly after the class. So the class, I imagine we have to show up in uniform. Like, are we gonna have to put our boiler suits on in between transitioning?
So basically, right after this class, you go to a 1 o'clock lab. Yes?
Yeah, yeah.
Okay. So yeah, if you go right from this class right to lab, yeah, feel free to show up in a boiler suit. That's totally fine. All right.
Okay, cool.
We're not in the fort. There's no regulation on that. All right. Show up in a boiler suit because there's no point for you guys to run back to your room to go to the ship. That's going to hinder learning. Just show up in a boiler suit. It's fine. All right. What a lot of people
Okay,
do
cool.
actually is, some people, when you get into what's called 503 lathe or 504, or 502, sorry, is welding. Some people take that class and immediately have to go to the fort. So what a lot of people do is they'll actually bring their khakis with them in their backpack, and it's just way easier to change out in the bathroom and head straight to the fort than it is to go back to the room, change out their boiler suit. So, all right. A little bit of information there. Any other questions? No? All right. Just a reminder, we have class Friday. All right. There is no class Monday. We have a quiz on Friday. End of day Thursday is pretty much the last time I'm going to be accepting anything for extra time in regards to Friday. All right. And again, come the next quiz or the next test, you have up until the day before. Okay. So let me know if you have it. Get Dr. Anderson to submit that form to me. So that way you always have the ability to use it. All right, it's going to be 10 questions. They're all going to be on Blackboard. I'm not using the lockdown browser. All right, it's going to basically look like an exam. It's not going to be one at a time. It's going to be one after another. Okay, it's going to cover everything as far as valves is concerned. All right. I think that's it. Oh, and it's all multiple choice, no writing. I don't want to read your writing. That takes too long to grade. All right. Everybody good? All right.
Good.
So, valve system nomenclature. Just a quick review. We have our isolation valves. Remember what we're trying to do. If we had a perfect world, we wouldn't need to, have valves except for just to move flow. But in reality, pumps need servicing, fuel heaters need servicing. We need to be able to close and isolate and work around these things. All right, so we have our isolation valves. All right. And we have our control valves. Same thing. We don't have a perfect world. We want to make sure that we have constant pressure. All right. So this is our automation valve. We may not always have 50 PSI or whatever coming out of this pump. There may be discrepancies. There may be above, there may be below. It all depends on what's happening. All right. How many burners are online? How much fuel is being utilized? It all depends. We want to make sure we have that constant pressure though. All right. If we look here, we have our automation valve. All right. This is the symbol for one. All right. As a automation valve or a control valve. All right. By the way, I've almost forgot to mention this. The valve PowerPoints is fully on the PowerPoints folder in Blackboard. So you have access to that since Monday. All right. We could see we have this dotted line all the way coming down and it terminates right here. That is the point in which we are sensing. All right. So that physical point, this valve is taking sensing from. All right. That's what that dotted line means. So regulating valves. We utilize regulating valves pretty much everywhere. This is an analog version of it. All right. There are digital ones that use little electric motors or solenoids or anything like that that we can fine tune, but this is an analog version. It does pretty much the exact same job. It just does it in a very mechanical way. All right. So you could see here, it says downstream pressure. All right. So utilizing that term, that's a new term for some of us. If we're looking at a river, all right, we're standing here on the edge of the bank of the river. That's you. All right. We have the flow of water going this way. We have our upstream and downstream. So at point 1 right here and point 2, what is happening? Actually, let me change that up. So at point 1, what is that considered? Is that considered upstream to you? Because remember, you're standing in this location.
Yes.
So upstream or downstream? So
Upstream.
point number 1 is upstream right now, which makes point number 3 downstream, right? Because it's in relationship to you. If you move the person and you go for a walk, you want to walk upstream, well, now you're at this physical location. So you're at location A. What is number 1 to you now?
Downstream.
Is it downstream? Or is it exactly where you're at?
In relation to A, you said?
In relationship to A, you went from a walk from B to A.
Oh, it's downstream then, right?
Number
you're
1
going-
is going to be exactly where you are.
Oh, yeah.
You are at this physical location in the earth now. So at location A, since you have changed locations, 4 is going to be upstream, 2 is now going to be downstream. 3 is still way the hell downstream, but it's still downstream. Make sense? It's in relationship to where you are. All right. So B's upstream is 1 and 4. Well, now you're at A. 1 is no longer upstream to A. And 2 is now downstream to A. All right. So that makes sense. Replace U as the valve. So we are upstream because this is where the flow is coming from in this location, number 1 over here, and downstream is over here at number 2. Replace yourself as this valve or whatever equipment you're referencing. There may be a pump over here, but number 2 to this pump, if you're talking about this pump, upstream is now number 2. Because the physical location of what you are referencing. All right. If you're referencing this valve, 2 is downstream. If you're talking about this pump, well, you are physically at that pump, well, 2 becomes upstream. All right. You see how the reference changes. It's all in a frame of reference. Just like if you were walking on a riverbank. If you are at location B, which would be our pump, all right, well, upstream is 1. Downstream is 3. If you change the location A, which becomes our valve, well, downstream becomes 2. Upstream is 4. That makes sense on this terminology that we're utilizing and the reference to what is going on here. All right, good, because we're going to be using that a lot here. So we are maintaining downstream pressure. This is a regulating valve. It's a little hard to see in here. You can kind of make it out, but I'm going to draw the bottom half here. So that's that bottom part of that valve. I'm going to redraw it into parts. All right. We have another color here. This is like a baffle. It's a piece of metal. It could be a gasket material. It's something flexible that can take high pressures. All right. And we'll go over that in a second. This is where it comes out and goes into the regulation. And we'll have our spring. Now, let's go red. Now we can kind of see a bigger picture here of what's actually going on. All right. It's the same thing. I just kind of blew up this area in here. All right. So we have upstream pressure coming in. Let's assign numbers to things because it's always way easier. All right. So our control, what will give us full control here is our spring. All right. So we're going to say the spring force is going to be 50 PSI or 50 pounds. That's what we're going to want. All right. And let's say, since we're in the downstream area, we have a 60 PSI. All right. So does that mean that we have 60 PSI everywhere or just in this one singular spot?
Just in that one singular spot.
We're going to have, yes, it's not going to be all the way downstream, but in this general area, we have 60 PSI everywhere. Remember, 60 PSI is not just a unit of measurement, but it's 60 pounds force over a square inch. All right, so every square inch, we have 60 PSI. So we have 60 PSI going everywhere. All right, so in here, we have 60 PSI going outwards to every single, I wish it would stop doing that, every single area.
Okay.
All right.
I
So
apologize.
60 psi is going upwards on this blue portion. That blue baffle can move. It can go up and down. It's like a piece of paper that sits there, and it will go and bend up or downwards depending on the force. Right? It's not a piece of paper, but it is a very strong piece of metal or gasket material. So if we have 60 psi pushing upwards on it, all right, think about it. Well, 60 psi can overcome that 50 psi set point of that spring, right? Because 60 is larger than 50. So if it can overcome that spring pressure, what's going to happen? What happens to that valve?
Seat.
I guess it would bend upwards, or the valve would push upwards.
The valve would push upwards and it would close, right? Because we could see where it's seating, correct? So it seats upwards. So that means we care only about the downstream pressure because that's the only spot where we're sensing. You can see our sensing tube right here. All right. That 60 psi that we're using as an example goes up. It pushes on that baffle. It pushes it up. That gasket material is getting pushed up. And it's overcoming that spring pressure. It's a larger force. And it closes our valve because our valve is attached to the bottom portion, that this blue area here. All right. So what we care about here, and every single regulating valve you can decipher using these three things. First of all is where the spring is. So the spring's action. Hold up, I just got an email. This might be a panic email from somebody. Nope. So we have our spring, which way the spring is facing on which side. All right, we'll go into it can change sides in a few minutes. The next thing is where it's taking its sensing from. So location of sensor. And 3 is which way the valve seats. All right. Is it upward seating or downward seating? It will change what will happen. And I just chose random numbers here. All right. You could always, you're on a test or a quiz or something, and this arises, what will happen to the valve? Is the valve going to close or open? Well, you can just assign numbers. All right. Any random number. All right. I'm using very large numbers. You can use negatives. You can do whatever you want. All right. But if you have 20 PSI down here and 60 PSI on that spring, what's going to win out on that battle?
60.
60, right? So 60 is going to push. It will overcome that 20 PSI and it will do what to the valve?
It'll close it.
It's going
Open
to
it.
open the valve because which
Oof.
way it's seating. All right. Remember, the flow is always going to go from below on these types of valves. All right. And we could see our seat direction is this way. If it's going to overcome that 60 PSI, overcomes that 20 PSI, it's going to push open that valve.
I have a question.
Yep.
About the diagram, is the spring, I mean the valve opening always going to be downwards like that, or it could be the other way where it pushes? Imagine it like, I'll turn my camera on. Imagine it like this instead of it being like this where it closes. You know what I'm saying? Or no?
So it's the opposite direction.
Yeah.
All right. So if we had a valve, instead of closing how it sees in this diagram down here, it went the opposite direction. So it went like this, right?
Yeah. Would it show that, and then we wouldn't have to think about it like too much differently, right?
So same steps apply. All right. So we look at the spring, we look at the location of the sensor, and we're looking at which way the valve seats. That's our third step in analyzing these things. All right. So again, if we have 60 PSI up on that spring, 20 PSI down here, that's sensing downward pressure. Well, 60 PSI is overcoming 20 PSI. and it will close the valve. If we change this from 20 and 60, we do it in the reverse. Let's say this is 30 down here and 20 up here. Well, 30 PSI will open. It'll open that valve and it'll overcome that spring pressure. And now this valve will open up, right? So we are always going to have above a 20 PSI, right? So we'd be maintaining our downstream pressure. But if we did that, what if it just came 40, 50, 60? It always kept getting bigger and bigger and bigger. That's why it's important that these things always work and they're going to regulate in both directions. All right, so we're going to keep this in this orientation. There's our seats. So if we look here, we have 20 PSI of downward force, 30 PSI of upward force. We're going to maintain at 20 PSI. So this is too large. We want 20 PSI. We don't want above 20 PSI in this instance. All right. So we have 30 PSI. It's too large. So it's going to close the valve. And if we change this down to say 10, and we still have 20 PSI because we utilize that pressure, well, that 10 PSI is not going to be able to overcome that 20 PSI spring force, and it will open the valve. And we're going to regulate perfectly at 20 PSI. It will always be 20 PSI on that other side. It won't be a huge amount above it, and it's not going to be below it. You see how changing the seat changed the entire way this regulates? If we had it face the other way and we wanted 20 PSI, well, if it got to 30 or 40 or 50, it would just stay open. It wouldn't matter because it would not be regulating it. It would just be above that 20 PSI. Makes sense?
Professor, I have a question.
Yep.
So if the pressure is greater inside like the bowl area, wouldn't it force the spring up, right?
Mm-hmm.
And that would that's closing the valve?
Yes.
Okay. And when you close the valve, wouldn't that increase the pressure on the inside?
So if you close this valve, remember
Or not
where
close it all the way, but
right? So we have its flow is going in this direction. If we close this valve, we're going to use whatever's over here. This is going downstream. It's being utilized. Hell, you could even say it's dumping overboard if you want to. I mean, it wouldn't make sense, but whatever is being utilized here, it's being used as an energy. All right. So as the pressure in this area drops, and we want to maintain, let's say 20 PSI up here, and we drop down to even 19. Well, that 19 PSI is not going to be able to overcome that 20 PSI. It's not going to be as great. It will be, and it will open up and allow pressure to come through. It'll allow fluid to transfer from one side of the valve to the other. And then once it's even and it hits a 20 PSI on both sides, well, it's going to maintain. It's going to maintain at that spot. Well, now we're going into 21. Well, 21 will overcome 20 PSI and it will close that valve. All right. This valve, remember where we're sensing, doesn't care about anything else but downstream pressure.
okay, so it's utilizing what's on the inside and it's not, okay, yeah, I get it.
So it only cares. The only information that goes to this valve is this point right in here. I know this is getting a little messy, so let's erase. It only cares about this point because where it's sensing right here. But if we were to take this line and drag it all the way down, all the way over here on this pipe, well, it would only care about this spot right here, right? Because that's the only spot in the world that this has any input from. It has a set point, yes, by this spring. This spring is a set point. But where its input from the system is only at the location. All right. So
I have a
remember,
question.
yep.
So the sensor part, is it the fluid or material that's going through it actually what's pushing up on the spring, or it's like a more like like electronic sensor or something?
So we'll get into that later in the class, but in this instance, yes, it's whatever the fluid is.
Okay.
All right. It's the physical fluid going up into that area. Come on, just let me draw an arrow. There we go. All right. So if we look here, we deciphered, yes, this is maintaining downstream pressure because we can easily see that fluid comes in from below. We could see where it's sensing. And it's maintaining downstream because in reference to this valve, this area over here is downstream of the valve. All right. So the regulating pressure is the closing force. All right. We could tell that by where it's acting. All right. The pressure comes in and it's acting below this black baffle right here, this black gasket material. All right. And telling by the way the valve seats, that's going to overcome the spring pressure and it will close it. And the spring is going to be the opening force. So when the spring pressure can overcome the pressure inside of where it's sensing, it will open up the valve.
I just have a quick question.
Mhm.
So obviously I see there's like thread rods in the nut, so that's how you would adjust spring tension, but how do you like tell how much spring tension you have on? Do they have like gauges or?
So basically what happens is that you would have a valve, and that's a good question, by the way. Yes, these, you can see this has a nut right here. This is going to go up and down via how much tension you, or how much force you apply to the spring. So every valve will have a range. All right. So if this one's directly, as other people have mentioned, this one is directly acting on what is happening inside of the system. All right. So this will have a range from like say 50 to 150 PSI. All right. And you never, as a designer, as a engineer who is in operations, you never want to hit these max and mins. All right. You always just want to stay, a little bit away from that. It'll give you that room because this may not be perfect. All right. So if this is somewhere between 150 PSI, that means that this spring and the length of this nut in this area can handle and regulate between 150 and 50 PSI in difference. All right. So depending on how much force is brought upwards or downwards or how tight or loose that nut is, you'll be able to go to 50 or 150 PSI. Knowing that if you want to hit, let's say 75 or 100, let's say, 100s right in the middle. Well, the way I would do it, I would install it. We won't really have a gauge, but I would put that nut right at the middle. All right. And then from there, we'd start up the system. You would bleed off basically the system. You would look at your pressure gauge and you would set it from there and try and dial it in perfect. All right.
Okay.
So we have a different version. So these are our two different versions that we can really have out there. All right. Again, we could see the spring is below. All right. So like we talked about, we have our three things that we want to look at. We have our spring. We have our location of sensing. And we have which way the valve seats. All right. So looking at this, the easiest way is just to assign random numbers. All right. Say your spring is 50 psi. All right. And we're going to say down here, we have 60 psi of whatever's coming in. It could be steam, water, it doesn't matter. So we're going to have 60 psi come up. So 60 psi of force is going downwards on that baffle material. And you could see right here, we're making contact. Okay. So it passes through the middle of that spring. This valve stem doesn't touch that spring. It makes contact with the top end. So if we have 60 psi of force going downwards, what happens?
It opens the valve.
It's going to open the valve. It'll overcome that spring force. All right. And if we don't have 60 psi, say we have 40 up here, what will happen to the valve?
It will open up the valve to allow pressure to close it.
So if we have 40 psi, it won't be able to overcome that spring pressure. All right. And it will close that valve. All right.
I'm just confused on how this one this unloading
Mhm.
valve is upstream because the arrow is going the same way as the downstream one. I'm just confused on how it's upstream instead of downstream.
So here's the thing that we're looking at. So this unloading valve, right? Just give me 1 second, guys. I'll be right back.
It's like based on where the sensor is, I think. So if the sensor is like to the left compared to the spring, it's upstream.
Yes, the other sensor is in front. You see how you have the one that's downstream, the one is behind the valve in the flow direction. You see that's how it's determined.
Oh, that circle with the arrow.
All right. Sorry about that, guys. So what's happening here is right here, the circle with the arrow is basically it's indicating a pressure indicator. All right. So what's happening is this major arrow right here is going through. That's just showing flow. All right. That's all that arrow shows. Now we could see where our sensor is coming from the upstream side of our valve. Remember, this valve is U, and in reference to where you are, the flow is going from left to right. Well, upstream is on the left-hand side. So we're going to say position 1. So we all say the same spot. So it can only sense on the upstream side. Well, that means that it's going to maintain back pressure. And back pressure is just saying that it's going to care only about keeping pressure on the upstream. All right. So the regulating pressure, which is on the upstream side, the position number 1, all right, is the opening force. It comes up, it goes down, and you can see this blue arrow right here is the force being applied and pushing downwards. And the spring is the closing force. It's going to be pushing, it's counteracting. All right.
Sorry,
That's
Mr.
what makes this. Say again?
I was apologizing because my laptop had just crashed, so I had
Oh,
to
you're
reset
okay.
everything.
Don't worry. So this spring is the closing force. It's counteracting the pressure that is happening where you're taking your reference from. These valves don't care about anything else than what they're told to care about. And that is one singular spot. This spot right here is all it cares about, regulating what is happening at that point.
Question.
Right. What's up?
For upstream, sensors, does it make more sense to have like downstream sensors because it's a lot less of tracking? Because I see like how much tracking that sensor has to do to get to the top of the valve.
So it doesn't matter how long it takes to get there. All right. And also, it's two different scenarios of what we're trying to do here. So right here on this one, let's say this is number one and this is valve number two. On valve number one, we're maintaining downstream pressure. So all we care about for whatever equipment is downstream of us, we want a certain type of pressure. All right. So it could be we're pressure regulating on this side of the system. We have 600 pounds force of steam. All right. And on this side, we want 150 PSI. All right. This is an actual situation on the ship. That's how we transfer from a 600-pound steam to 150 auxiliary steam. All right. So we don't care about 600 PSI on this side. This side can be doing 150. It could be doing 660. It could be doing whatever the hell is going on this side. But all we care about is going to this side and to this equipment is 150 PSI. All right. Whereas over here on valve number two, the unloading, the maintain of upstream pressure. Well, we may be in a spot where we want a certain amount of back pressure. All right. We may want to make sure that if we have a heat exchanger, that we have a certain amount of pressure inside of it. All right. So that way it doesn't get like airbound. It doesn't get, it's utilizing it's always full of fluid. All right. And this dumps overboard. Well, if it's a pipe that just leads overboard, we don't care about it. We care only about what's happening on the left-hand side. All right. So this comes down to what equipment you have on either side. What are you trying to accomplish utilizing these valves? All right.
So can these work in conjunction? Like, can you have two of these set up, like one behind the other or one in front of the other, for whatever reason?
I mean, you can have it on two different. If there's a situation that needs it, there's no reason you don't have to have it, because it only matters what's happening at this point.
Professor,
won't work.
I'm sorry.
It's okay.
Can you throttle these? Or like, would you want to?
They are going to throttle themselves. They're not going to be fully open or fully closed.
Okay.
All right. So these will be a throttling valve where they might be at a certain point 25% open, 50% open, 100% open. All right. So if you're starting up the system for the first time ever, well, let's stick with this. We have 600 pounds steam over here and we want 150 over here. If we're starting the system up for the first time, we're just starting to make pressure over here. So we start at 5 PSI, 10 PSI. I'm not going to bring you all the way through it, but we get all the way up to 600 PSI. Well, as soon as we start to do this, what's happening over on this side? We have 150 PSI of what we want. So once we hit 600, this valve is going to basically close up over here until 150 drops below. Then we need to start adding more steam into it. All right. So as we're bringing that system up, this side will come up at the same rate as the 600 will come up until this side hits 150. All right. So we can think about this in two ways. When it's starting up, these things will be, opening up. So let me draw a graph for you so it's easier. So this bottom line is 0% open, and all the way up here is 100% open. All right. Now, if we think about it, let's say in this new example, what makes this work optimally, or where it's going to throttle in its best position, let's say it's 50% open. So when the system starts, this valve is going to be 100% open, right? Because we're going to be wanting to have 150 PSI over here. But when the system starts, there's no pressure. So there's no closing force. So the spring has this thing wide open, right? So we start at 100 PSI and as an 100% open. So as we go down, we start to regulate. So we start closing the valve slowly and slowly because we now have a force counteracting the spring. So as it gets to 5 PSI on this side, it will counteract that spring force just a little bit more than 0 PSI was. As we get up to 10, 15, we get up to 100 PSI, we're going to be counteracting that spring force more than 0 was. So what will happen is this will come down and it will dive down to get closer and closer to 0% open, but it will never go down to that low until we surpass 150 PSI. So what will end up happening is these things will look mostly like this. They'll start to slowly get themselves into a spot where they'll go all the way open, then they'll start to get closer to closed, and then as the system comes online, it will even itself out. Okay, remember, these aren't just one image of what's happening. These things are constantly moving, right? They're constantly regulating. That's what makes automation so nice, because otherwise you would have to be staring at that pressure indicator and sitting there with a valve yourself, manually opening and closing this valve every single time the pressure changes. All right.
So are these valves like constantly going from open to close, like multiple times a second or whatever?
They will be constantly changing their position, whether it be open or close. Remember, these things can throttle, so they'll throttle to a certain percent open or a certain percent closed. All right. Sometimes they may be always closed. Sometimes they may be wide open. It depends on what's happening in the system. But when we look at it and we can take a freeze frame and we pause what's happening in the world and we apply numbers to here, we can determine what happens. But we always have to remember that this is a constant in motion. It's constantly changing. If it wasn't constantly changing, we wouldn't need pressure regulating valves. All right.
Okay.
Does that make sense to everybody? Okay, good. Remember the 3 things, and if you freeze frame this, 3 things: spring, where it's taking its sensor, and which way the valve seats. All right, you know those 3 things, apply some random numbers to it and see if it works the way you think it does. All right, and then flip those numbers around, make one high, one low, and then go back to the other one being low and then high. All right, if it still works to the way you think it needs to work, then the valve works. All right, and you can determine everything that happens just by applying those random numbers.
Is it ever really set with the seat the other way, flipped upside down, like we said? Because you can't really regulate, how much, like that can go just wide open. Because the seat in this orientation will shut at a certain point.
Well, it all changes. So it's one of those things where if, I encourage you, if you guys want to just play around with these different ways of doing things, where if you have the seat as it is right now in here, but instead we sense on the top from this side, well, we're concentrating on downstream. Will it make sense, or will we have to flip this valve around? I don't know. We would have to go through with it and figure it out. This is just one instance of these valves looking like this. All right.
Okay.
Coming up, you'll actually see schematics of actual valves. So we have our control valves, which is a constant pressure regulator, and we have our fuel oil pressure regulating valves. All right. Again, if we look at this, we have a new thing here. We have a dotted line, but it doesn't access a point. All right. What's happening is we have a control air signal. All right. We use on our school ship some of the worst fuel you can get your hands on. It's literally one step above asphalt. All right. So we don't want that getting into the crevices of our regulating valves. All right. It will not allow these valves to function really. So we use air. All right. And what happens is, as you can see here, we have two different types of air regulating valves. All right. So this one is downward seating. You can see how this opens. We have the little crevices right here that allows for the steam to pass. All right. Over here and over here, we can see where it's seating. All right. We could see the operating air pressure from the control pilot, which I'll explain in a second, comes in this port right here. Come on. And it fills this crevice up here. We could see our spring is existing in this spot here. And it's downward seating. This one is upward seating, so we can actually see it change. So the spot where it seats is right there and there on that angle. All right, so that's an example of these two things changed. All right, so a direct acting is coming in from above. And then we have indirect acting, which comes in from below. All right, so two different types of valves. So we also have a fuel oil temperature regulating valve. So we utilize steam for our heater because it's a steamship. We have a lot of steam. Well, we want to heat up our fuel, all right, in order to make it move. All right. So we want to make sure we constantly are regulating the temperature. Like we said before earlier on Monday, if we can detect it, we can measure it, we can create a automated signal off of it. All right, so we have our sensor over here. That sensor puts information into what's called a pilot valve, and that sends out a signal to our actual automation valve, our control valve. All right, so this is a pilot valve here. All right, what happens is we have a high pressure steam signal, high pressure steam coming in over here. We want to reduce steam pressure over here. This that I'm drawing out is our actual valve. All right, that's the automated valve that we were looking at earlier. All right, so right here, we are taking a pressure reading. All right, I'm not going to get into, nor am I going to expect you guys to know how that happens. That's for later on. This is going to take a controlled pressure reading off of it. That is going to go into our control pilot valve. All right, so our control pressure is going to go in, and this is our input. All right, we have an air supply that comes in. That air supply is a compressed air. We have compressors on the ship that will only supply a certain amount of air to our air regulated control valves. All right, so when you're using needle guns, or if you're utilizing any sort of like pneumatic air tools or anything like that, that comes from a completely different air supply. All right, so we have a designated air supply that comes in. Let's call it 100 PSI. All right, and now it's going to have a ratio. All right, it will have an input, and it's going to determine off of that input how much of this air supply it needs to send to control this valve. All right, that's what's going on here. We have our only input that will take our air supply and send that air supply pressure to our control valve here. So that way our control valve stays clean. That way if we wanted to do this with temperature, we could do the same thing, and it would be able to still send an air pressure that is going to be determined. It's going to be, like I said, it's a ratio that is predetermined by the person that designed the power plant. All right. So that is how we can take temperature, we can take flow, we can take pressure. Like I said, if you can measure it, utilizing these controlled pilot valves, we can send that signal and we can actually automate it. All right. Does that make sense?
Yeah, so in the controlled pressure line coming from like on the output of the control valve, like when it goes to the controlled pilot, is that the fuel oil that's running through there?
It's may or may not, depending. So some instances the designer may, because it might just be steam. All right. And you don't want to burn up what's in here because it's steam. All right. And this can take the higher and hotter temperatures. Another thing that could happen is that it could be sending this control pressure. Let's say if it's fuel, there might be a device here that it moves a little bit. All right. It has a very small baffle and it's right on there. And this control pressure might only be 5 PSI of pressure. And it might be a very sensitive line that comes through. All right. So every instance it can change. So sometimes this might be, yeah, just straight steam that comes into this control valve. All right, this control pilot. Most of the time it's going to be some sort of a controlled pressure that comes off of our measuring device. But at the same time, you can also have things that come in and you would actually have true pressure coming in here. All right. So both are true. Other things, like I said, temperature, flow, level, so much can be put into that. All right. If it's something that can be measured, we can turn it into an air signal. All right. That's our control valves. We have a couple of other different valves out there. We have a normally closed valve. All right. That means in its everyday existence, it is closed. All right. It only opens when a certain condition arises. All right. So that would be a relief valve. You would want a relief valve to be closed all the time. If that was on an air tank, you wouldn't want that thing just blowing air out, right? That would be counterproductive to what's going on. So you want that valve to normally be closed unless this certain condition happens. So same thing right here. This symbol right here represents a relief valve. The other way that I showed you guys the other day that can be drawn is that. All right. So that is our relief valve. We can see it's taking in from our pump and it goes into the relief valve. But notice on the other side of the relief valve, we have an arrow that draws back into the suction side of our pump. Why would we want to do that? Why wouldn't we just put a, why would we want that? Why wouldn't we just blow it out to the environment overboard? If it's a problem, why would we want it to go back into the system?
It's more efficient.
So more efficient. What about fuel?
Maybe you
put it in the ocean.
We wouldn't want to put it in the ocean, right? So
You
what if
could use it?
we could use it? Think about you. You as an engineer, you come wandering over here and you come looking down at this pump, and it just so happens that your relief valve is right at eye level, and then all of a sudden, you know, that pump was making some funny noise. So you look at it, and all of a sudden you get sprayed in the face with some hot fuel. Not good either, right? So, oops, geez. With pumps and certain systems, relief valves will always go back into the suction side of the pump. All right. Just because it's on the suction side doesn't mean that we're going to have fuel going in here and now whatever's coming in and we're getting all of a sudden 2 times the amount of fuel. That's not how that works. We'll talk more about that when we get into pumps. But all it is that this will become a little tiny little service itself, and it will just constantly be recirculating around itself. So it will be fine. So don't think that all of a sudden we're going to have double the amount of fuel trolling through here. All right. Now, if this was just air or if it was an air tank, yeah, that'd be no problem. It would just go out to atmosphere. We took the air from the surrounding atmosphere and it went into a tank and the tank overpressurized, so it goes back into the atmosphere. No big deal. We don't want fuel to all of a sudden go and dump into the bilge and now we have a bigger problem. It's way easier for it to just stay where it belongs, which is in the pipes. All right. Again, that's a normally closed valve. All right. Then you have the opposite. You have it also normally open. All right. So everyday condition, everything that's happening, it's always open, and a singular condition will bring it to closed. All right. We have two different pictures here. One is a relief valve. Remember, relief valve opens and closes at the same pressure. And we have a safety valve. A safety valve will open at a certain pressure, and then it will close at a pressure below that set point. All right. Now we have something called a bypass valve. All right. Bypass valves are going to be around pieces of equipment that we want to be able to bypass. All right. So if we're sitting here and we're not a school ship, let's pretend we're an actual cargo container. All right. Well, this meter here, that all it does is meter fuel. What if it gets clogged? What if we get some bad fuel one day, or the little plastic propeller in here that actually meters the fuel breaks? All right. We don't want that sending those little plastic bits into the burners or anything like that. And at the end of the day, measuring the fuel is not the most important thing in the world. That just shows our efficiency and it goes to the company. We don't really care. But in reality, if we didn't have bypass valves, would we want a meter to shut down our ability to go across the ocean? We have a timeline. We have cargo that needs to get somewhere. Someone's Amazon package is on that ship. That's why we have bypass valves. We can close our isolation valves, our input and output, our inlet and outlet to our meter. And we can open our bypass valve and now allow the flow of fuel to go around the meter. And we continue to steam. We can now service this meter. When the meter gets put back in online and it's all fixed, we can close our bypass and open up our isolation valves. All right. Now, do not do this. Would this work as a bypass valve? Would we want a bypass valve that is on the inside of our isolation valves?
No.
No, because it wouldn't work, right?
No, it would not work.
All right. So make sure you pay attention to when you guys get out in the field. All right. Finally, we have something called recirculating valves. All right. And recirculating valves exist in fuel. They exist in other systems as well. Recirculating valves are important because we need a certain amount of fuel pressure. All right. And if we don't have that fuel pressure, well, or a certain amount of fuel flow, then that's not good. So it's one of those things where diesel engines have this, steam engines. If we're only operating, we're doing startup and we're starting up one burner. Well, we still need the same amount of fuel pressure going to one burner as if it was four. So would we want a pump to go on and off, on and off, on and off, or a regulating valve to open and close like crazy? It'd be way easier to maintain a certain amount of pressure here and just recirculate it, any unused fuel. They do it on diesel engines as well. All right. It maintains a certain amount of fuel pressure going in. So that way every single cylinder gets the same amount of fuel pressure, no matter how hard the engine's working or what RPM it's at. Any unused fuel goes right back to the fuel tank to just get recirculated back in. All right.
Sorry, what does it maintain?
Maintaining a certain amount of fuel pressure. All right, no matter how many burners that we're going to be using.
For the relief valves, it was just normally closed and normally opened, right?
They're
Those were
going
the
to be
two?
always, so relief valves are always normally closed.
Okay.
Normally open will go into when we get into water making, but just know
Okay.
that does exist.
Okay, thank you.
All right. So any questions on valves?
Are we gonna have to know the symbols for the quiz? Of like all the different kinds of valves?
I'm gonna say no. All right. I am introducing the symbols for valves slowly and all other systems. I am going to be posting soon the standard symbol tracings that we all use. One of those things that I always keep handy. All right, if you don't have them memorized. All right, you're going to expect it to use those when you do tracings and things like that. And when we get into pumps, it's going to become very mandatory to know them. All right. So it's not something you should know for test. It's pretty much one of those things I can guarantee you know for life. All right. If you're going to be in this industry, that's something you should definitely know. All right. Any other questions? Nothing? All right. Remember, guys, we have a quiz on Friday. All right. Make sure you get into class on time. Quiz is going to start directly at 10. Okay. It's going to be on Blackboard in the quiz section. It's going to be 15 minutes, 10 questions, all multiple choice. You're going to have your Zoom on. I'm not using the lockdown browser, all right, because from what the other class told me, that doesn't allow you to work Zoom at the same time. And pretty much, if you need the extra time, or if you just want to have it just in case your extra time, Thursday night is the last time you could tell me. Everything's going to be set up by that point. So, all right. All good?
All good.
Sorry. So we have we have the quiz at 10, and then we come and then we're on Zoom, and then we come back at 11:30.
No, I'm sorry.
For actual.
The 11:30 is the quiz. Your
Okay,
class
so-
time is when the
Okay,
quiz
that
is.
makes
Yes,
sense.
yes. You guys are all good. I'm 3 classes a day of 5:40. So your
Good.
class time is always where you're going to have your quiz. Thank you for bringing that up. Your quizzes are always going to be in your class. Your tests are always going to be on your examinations. Your tests are always going to be in your physical class. All right.
And you said you posted a PowerPoint with all the valves on it, so we could study that?
So I'm going to post the PowerPoint is always posted. All right. But you'll have it before the quizzes. You'll have it before the test. The class is pretty much designed so that way you'll have a full week between the last piece of material of what you're going to learn for the exam, and you'll have a full week before the actual test. So for example, test number 1 is February 10th, and you will learn everything by Wednesday the 3rd, which gives you a full week to study. All right.
Okay, thank you.
And then let me see. Let me pull this up for you guys so that way you can see it. And then this is the standard symbols for tracings. All right, so I'm going to be posting this. Again, this is just something you'll need to know. All right. And they'll start to make sense, like kinetic pump and turbo pump and all that kind of stuff. Strainers, we'll slowly make our way through this. Okay. Don't worry about copying this down. It'll be posted to Blackboard. I'm not that mean. All right. There's no more questions. You guys are all set for the day. I will see you on Friday for the first quiz. All right.
Thank you.
All right.
Thank you.
thanks.
Thank
Thank you,
you.
Professor. Have a
Have a
great day.
Thank you.
Thanks a bunch, Mr. Callahan.
I had a question, but I don't know if you would know about this or not.
Okay.
I just wanted to ask if you knew if we needed to, we needed the meteorology course to be able to go on cruise or not, because I haven't taken meteorology yet.
I am not going to say yes or no because I actually don't know. All right. So,
Okay.
are you so you're Marine Ops Deck then, I'm guessing?
Yes.
Okay. You're second class?
I'm a third class.
You're a third class. I always forget when you guys take this, or supposed to take it.
We're supposed to
You
take
were
it this
supposed to.
year.
So you were supposed to go on cruise this past summer for your freshman cruise.
Yes.
I don't think you need meteorology for your mug cruise, unless you plan on doing a double cruise. You
I'm
might.
not.
Okay. I would check with your mate, whoever your actual advisor is. That's an advisor question.
Okay. All right. Thank you.
All right.
Have a nice day.
Have a good one.
Hey, Professor.
How you doing?
I'm doing good. So I just wanted to be clear, right? So you have the pressure regulator on the unloading, right?
Mm-hmm.
And so the pressure regulating maintain the downstream, which that the spring pushes downward, right? And the downstream pressure pushes upward, which open the valve.
Here, I'll bring it back up. So what we have here, all right. So to maintain downstream pressure, our pressure, you can see my mouse, right?
Right, yes.
Okay, good. So our pressure, our downstream pressure is going to be the closing force. So it's pushing up against that spring, all right, which closes the valve because that valve is going to be seating upwards. All right.
Okay.
So the spring is the opening force because it's counteracting. All right. It's on the opposite side of our pressure. And that's going to be opening the valve again because the valve is upward seating.
Okay.
But that's just for this type of valve. All right.
Okay.
So that's what I was saying. Every single time, if you look at these things, always look at your spring, always look at where your sensor is, and always look at which way your valve seats. But this is a perfect example of maintaining downstream pressure. This is the most optimal way of doing it. All right.
Right.
So in our unloading or maintaining upstream pressure, we want to maintain that upstream pressure. We want to concentrate and sense that upstream. So that's where our sensor is coming from. It goes above, so it's again counteracting that spring.
So it goes from T-reg, it goes up to the top.
Mm-hmm.
Okay, and then it goes back down.
So it goes up to the top here, and it's on that baffle, that black piece of material, that gasket material right there. All right.
Okay.
And it's going to be pushing downwards, and it pushes downwards, and it will open up that valve. And the only thing that will close that valve is that spring.
Oh, that is pushing upward.
Exactly.
Okay.
All right.
Okay. All right, Professor. Thank you very much.
No problem.
All right. Have a good one. All right.
You as well.